So welcome to CHS Math Help. We're covering our topic is optimization, which in calculus terms, it's finding the extrema of a graph using real life examples. So one of the first things we'll start with is example one. It's find two numbers whose sum is 60 and whose product of one times the square of the other is a maximum. So that was confusing, so we'll write it out. So find two numbers, we'll use x and y, whose sum is 60. So our first equation is going to be x plus y equals 60. And then whose product of one times the square of the other is a maximum. So the product of one times the square of the other is the maximum. So the first thing, we have two different variables, and when we take the derivative, we can't have that, so we need to combine the two equations. You should always start with two equations and then find a way to combine it. We'll solve for x on this one, since when we combine it into here, it'll be easier. So we'll have x equals 60 minus y, and then we'll plug that into here to get 60 minus y all times y squared. And so after we combine that, we'll have 60y squared minus y cubed. And so this is going to be your graph. Okay, so the graph of this is going to look something like this. So you'll have two extrema, you'll have a maximum here and a minimum down here. Now the problem is asking for a maximum, so this is the part that you're concerned about. Now for these 2 points, the derivative is going to be 0. So the slope of these 2 points is going to be 0. So that's why we need to take the derivative, because the derivative is the slope of this function right here, so then we can find what points the maximum is at. So when we take the derivative, we'll have 120y minus 3y squared. And then since this is the derivative, the slope, we'll set it equal to 0. And then so this is what we end up with. And so you can see the two zeros, it'll be 0 and 40. So here is where we set up our line, our first derivative test. So then this will be at prime. And so you'll have 0 and 40. Now, since you can't have anything be less than 0, and these two add up to be 60, those are going to be your two bounds. So you don't have to worry about anything being past here or past 60 here. So what we'll do is in between these, just plug in any number. So for example, you can plug in 1 or 20 or anything between here, it doesn't matter. So if we plug in 1, you'll see that this would be 1, and then it's obviously going to be positive, so it'll be positive here. And then if you plug in anything between 40 and 60, you'll see that this will be greater than this. So wait, is that true? No. You'll see that this value here, the squared value, it'll overpower this 120, so then it'll be negative. So here it'll be negative, and if you think about, these two represent the values of the slope. So here it's going up, and here it's going down. So it'll look like that, and that's the value that you're trying to look for. So at 40 is where you'll have your maxima. So you'll have your y equals 40, because that's where it's the maxima at. And then you plug it back into one of your original equations to get the other value. So we'll use this equation here, because that's easier. So x plus 40 equals 60, and then x is obviously 20. So those are your two values so that you get the maximum value. So for here, we found the two values that gave us the maxima, which is optimizing it. We're trying to find the highest or lowest value.
Yeah, I'm ready.
You started?
Mm-hmm.
Okay. Here. So for our next example of an optimization problem, we are going to be given a 8-inch long pipe cleaner, so 8 inches, and this pipe cleaner is going to be bent into a rectangle. And I'm going to label this dimensions x and y. And what we want to optimize for here is area. So we're looking for the dimensions of this rectangle that can give us our maximum area. So as we know, area of a rectangle is equal to just the base times height, so in this case, x times y. And we also know that this rectangle is formed by the bending of this pipe cleaner. So the pipe cleaner is 8 inches long, therefore the perimeter of this rectangle, should be 8 inches. So our perimeter is going to be 2 times x, we have x here and y here, plus 2 times y. And we also know that this is equal to 8. So if I just forget about this perimeter right here, and I solve for one of these variables, let's pull out this 2, you get x plus y equals 8. So we have x plus y equals 4, and that's a really simple equation that we're pretty familiar with working with. For optimization, the first step that we usually try to do is try to get ourselves, well, one, identify a situation, and then your second step here, try to get your 2 formulas, your 2 equations that you can use to optimize. And so here we're trying to optimize area, and we have 2 variables here, so you want to get rid of one of those. So we're going to solve. I'm going to solve for y. So y is going to be equal to 4 minus x. And now combining these 2 equations, I'll get that my area is equal to x times y, which is 4 minus x. And that is going to be equal to 4x minus x squared. And that's our area, which is what we're optimizing for. In this case, we're trying to optimize for maximum area. So if we have an area graph, x, y, it's gonna, we want to look for a maximum here. And so we want to first step here is going to be taking our derivative of our area equation. So I'm going to label this a prime. Derivative of 4x, it's 4, and negative x squared, so negative 2x. And now I want to find my maxima. So I'm going to do my first derivative test here. I'm going to label this number line a prime. And first I want to see where a prime equals 0 or where a prime does not exist. So if I graph this, it would just be a line, and so it's not going to really exist anywhere. So you might actually want to write that as a prime does not exist. So, but what I'm really going to be concerned with is when a prime equals 0. So I'm going to set my derivative equal to 0. And from solving, I see that x is equal to 2. So I'm going to put a 2 on this number line here. And now if I go less than 2, let's use 1, and plug that into my derivative, a prime of 1 is equal, well, 2 times 1 is 1, 4 minus 2 is 2, so that's going to be positive. So we're just going to put that it's greater than 0. And now for a prime of a number bigger than 2, should be 3. So 3 times 2 is 6, 4 minus 6 is negative 2, so say that that's less than 0. So from 2, anywhere less than 2, we used 1 in that bounds, and we found that that was greater than 0, so positive. And for anything greater than 2, we used 3 in that bounds. We found that the derivative was less than 0, therefore it's negative. And so at point 2, we see that the derivative changes from being positive to negative. You'll find a maximum. So what I solved for here was at x equals 2, we found maximum area. So if x equals 2 and our x plus y equals 4, that means we plug this in. Hopefully everyone can see that y is also equal to 2. And if we take our area here, 2 times 2 is 4, and so our maximum area here we see is 4. I think that's it. I really hope that's the right answer.
Yes, sir.
Good. So for this third and final optimization example, we are going to be trying to find the point on the curve y equals x squared that is closest to the point 3, 0. So just for graphical representation, y equals x squared is going to look a little something like this. That's horrible parabola, but whatever. And I'm going to put 1, 2, 3. I'm going to make this point 3, 0 here. And so what we're looking for is the distance to this graph. We're looking for some point on this graph that has the smallest distance to point 3, 0. So if we're familiar with the distance formula here, that's going to be our first equation. Here we're optimizing for distance, looking for a minimum specifically. So our distance is going to be equal to the square root of y minus, and we'd say y2 minus y1, and our y here is 0. And we're square that, plus, and we're going to take our x minus this x, which is 3, squared. And that's going to be our distance formula using from points from this graph to the point 3, 0. And the reason that I put the 0 here and the 3 here with these x's is because we're measuring our distance from those points. And so if I want to rewrite this, I'm just going to d equals the square root of y squared plus x minus 3 squared. And we also have this other equation given to us. So we know that on the point that we're going to find, y is going to be equal to x squared. And that gives us all the points in our parabola. And we also have our distance formula here. So if I want to be able to take a derivative and optimize for distance, I need to get rid of one of these. So let's, oh shit, I should restart. Actually, I should probably get rid of the square root first.
Yeah.
I'll say that first. So in this case, we're going to be optimizing for distance here, and I'm going to want to take the derivative. And as many of you calculus students may know, it's a lot easier to take the derivative of an equation that doesn't have this square root over it. So we're going to be optimizing for distance. I'm going to say that our distance that we find is going to be equal to a. And let's say distance a is less than distance b. And so I think we can all agree that a squared is also going to be less than b squared. Correct me if I'm wrong, that means I can just get rid of this square root here. And the distance we're looking for now is just going to be y squared plus x minus 3 squared. The reason I'm doing this is because if we find the smallest distance, it's also going to have the smallest square root. And the largest distance is still going to have the largest square root. So we don't really need this square root. We're just adding an extra calculation that we can just get rid of. And now, so we had our two equations here. We have a distance and we have a parabola. So I want to get rid of a variable. I'm going to go ahead and get rid of this y here. So y, we know that y is equal to x squared. So I'm going to rewrite this. D equals x squared plus x minus 3 squared. And I'm going to expand this. D equals x to the 4th plus, this is x minus 3 squared, so I'm going to have x squared minus 6x plus 9. And that plus is just going to carry over, and I'm just going to take my derivative from here. So derivative of my distance now is going to be 4x cubed plus 2x minus 6. So now that I have my derivative, I want to see where we could see the least amount of distance. So we have our point 3, 0 here, and right here the point is 0, 0. That's at the origin. And so I'm going to make this my domain. The reason I'm going to do this is because we know that no point to the right of 3, 0 is going to be the smallest distance, because all of these are going to be a smaller distance. And we know that this here could also, from the distance from the origin to this one, to the point 3, 0, could also be the smallest distance. So I'm going to use those as my endpoints here. And as we saw earlier in our optimization problems, we see our maxima and minima at our zeros of our derivative here. So I'm going to set my derivative equal to 0, and let's solve this. And we can pull out a 2 here, and we're going to get 2x cubed plus x minus 3 equals 0. So what I did is I pulled out the 2 and just divided the 2 over. And there's going to be ways to solve this out, but I just want to put a little insight. 2 times 1 is going to be 2. Let's say x is 1 minus 3. That's going to work out. So a 0 of our derivative here is going to be that x equals 1. So now we have 3 points. We have our endpoint of 0. We have our endpoint of 3. And then we have our 0 of our derivative, which is 1. And so if we put in the distance of 0, distance of 3, and distance of 1, let's put it into this problem here. With the distance of 0, we're going to get distance equals 0 squared, this is 0, plus 0 minus 3 squared. 0 minus 3 is negative 3, squared is going to be 9. And we do d of 3 here, we're going to get 3 squared, which is 9, squared is 81, plus 3 minus 3 squared. So 3 minus 3 is 0, squared, plus 81. It'll be 0 plus 81, which is 81. Now d of 1 is going to be 1 plus 1 minus 3. 1 minus 3 is negative 2, squared is 4, and 4 plus 1 is 5. So we see that the smallest distance here is when x equals 1. Keep in mind, this isn't the distance from the point 3, 0 to the point of 1, 1. This is actually that distance squared. So the real distance of 1 would be the square root of 5. Because the distance formula, as we know, is the square root of all that, but we removed this sign earlier. But anyway, our answer would be that the point on the line 1, 1 will give us the smallest distance from the point 3, 0. And I get this point 1 run from simply plugging in x equals 1 into our original equation y squared, y equals x squared, so y equals 1. One final note, in case anyone is confused as to why I simply just use the endpoints here, we have a closed interval. Now, as I mentioned earlier, the distances we saw could be from 0 to 3, and so I included 0 and 3 in our interval here, and we make that a closed interval. Whenever you're testing for maxima or minima on a closed interval, you need to test the endpoints. So we tested 0, 3, and then we tested the 0 of our derivative, which is 1, and we came to find that the point 1, 1 yields the smallest distance from the point 3, 0. I think that's English. I started recording, so.
Alright. So welcome to La Hospital. This is a way of evaluating limits that would otherwise be impossible to use to evaluate using algebraic techniques that you might already know. So we'll start off by doing an example. It's the limit as x approaches 0 of e to the 3x all minus 1 all over x. So first thing we'll do is plug in 0. You'll see that e to the 3 times 0, that's e to the 0, which is 1. 1 minus 1 is 0, and at the bottom, that's just 0 as well. So here we have an indeterminate, 0, 0. You have to make sure that it's either 0, 0, or if this goes to infinity, it'll be infinity over infinity, because otherwise L'Hopital's will not work. So it has to be either like this or like this. Now, what L'Hopital's rule says is that so what L'Hopital's rule says is that the derivative of the top and bottom is the limit of the derivative of the top and bottom will equal the limit of just the two functions. So we'll take the derivative of the top and bottom separately. So the limit as x approaches 0. The derivative of this will be 3 e to the 3x. And then the derivative of the bottom will just be 1. So now we can try plugging in 0 again. So this will be 0, so e to the 0 is 1, so then 3 times 1 over 1, that's just 3. So we can see how evaluating the derivative of the two functions will get us the answer to the limit. And you could check that with the calculator. If you use a table, you'll see that from both sides, this function here will approach 3. So another example we might have is if it's coming from one side, if the limit's from one side. So we'll have the limit as x approaches 0 from the positive of sine x over x squared. Now if we try plugging in 0, you'll see that the sine of 0 is 0, and then x, or 0 squared, is also 0. So here we have an indeterminate 0 over 0. So that means we can use L'Hopital's rule. So the derivative of sine x is cosine x. So we'll have the limit as x approaches 0 from the positive of the derivative cosine x. And then the derivative of the bottom of x squared is 2x. Now, okay, so what was it?
You get a 1 over 0, so it's just infinity.
1 over 0, which is infinity. Is that the answer?
Yeah.
Infinity? Ah, crazy. Okay, so now for this, if we try plugging in 0 for both of them, we'll see that for cosine x, you get 1, And then for 2x, 2 times 0, that's just 0. Now, 1 over 0, if you think about dividing 1 by a really small fraction or a really small decimal, like 1 divided by 0.0001, you'll get a really big number. So as you get closer to 0, it'll become infinity. Now,
Go ahead.
Hey guys, thanks for watching this episode on optimization. Don't forget to follow us at Chino Math on Twitter, and if you have any other suggestions that you'd like to see videos made of, go ahead and DM the Twitter account or just see me or Alec personally at school. Thank you.
Alright guys, my name is Eric Chavez and I approve this message.